My name is Rajesh Prasad. Today I am going to discuss on how to solve the recurrences, method of solving the recurrences. So what I am going to cover over here that I will define the recurrence relation and we'll discuss on various solutions to solve the recurrence relations. So first one I will discuss on method of characteristic equation, and then very popular method master method, and next one will be recursion tree, and then we'll discuss a special case of changing the variable. So why we need recurrences? We know that if you are interested in finding out the running time of any procedure which is involving iterations, like see here for I equal to 0, I less than n and I plus plus. Suppose we are interested in finding out running time of these recurrences. We know that loop is going to execute n plus 1 time. So this its running time will be n plus 1. But what about a program which is involving recursion? So if a program is involving recursion, we can't find running time of the program using loop and other method. So we have to solve the recurrence relation. So in general, what define recurrence relations? That nth value is actually written in terms of previous values, right? See this, xn is written in terms of n and xn minus 1 and any up to n minus k. So for example, tn is written in terms of tn minus 1 plus 1. So that means nth value is being expressed in terms of previous value. So this define recurrences. For example, if we define tn equal to tn plus 1 plus 1, so this is not a recurrence because nth value is not being expressed in the terms of the past values. So how to solve this kind of recurrence relations? So there are many methods. So first method I will discuss about method of characteristic equation, followed by master method and other methods. For example, suppose we want to compute the Fibonacci sequence, right? So its definition is Fn is Fn minus 1 plus Fn minus 2. We know it. And F0 is going to be 0 and F1 is going to be 1. So in general, in method of characteristic equation, we transform this to Fn minus 1 minus Fn minus 2 equal to 0. So what is objective? Objective is to solve this Fn in terms of n. So you know why it is not very convenient? Because if you are interested in finding out F10, we have to compute the previous value. So what is objective of solving the recurrence relations? That F10 can directly be expressed in terms of n. So that if you just put value of n equal to 10, you can get the answer directly. So see this. So this is also recurrence relation. So let's have idea of this recurrences by characteristic equation. So we have two type of recurrences over here in the method of characteristic equation. One is homogeneous recurrences and other is inhomogeneous recurrences. So homogeneous recurrences is of this form: a0 tn plus a1 tn minus 1 plus and dot 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 ak tn minus k equal to 0. That means in this situation, right hand side equal to 0. So for example, if see this Fibonacci sequence, Fn is written in terms of Fn minus 1 plus Fn minus 2. And you just write down like this. So in method of characteristic equation, if Fn is being written like here, minus Fn minus 2 equal to 0. And in this situation, we write Fn equal to x to the power n to solve it. Our objective is to solve this. So xn minus 1 minus xn minus 2 equal to 0. Clear? and take the lower order term outside. So this will become x square minus x minus 1 equal to 0. So objective is that this is not equal to 0. So this will be 0. So x square minus x minus 1 equal to 0. Clear? So if we solve this x, we will be getting 2 root 1 plus root 5 by 2, and other root is 1 minus root 5 by 2. Clear? So we have x1 and x2 2 roots. So solution of this recurrence relation is given by Fn equal to c1 x1 to the power n plus c2 x2 to the power n, when roots are not repeating actually. So here roots are not repeating. So this is the solution. So so Fn will be given by c1, where x1 is 1 plus root 5 by 2 to the power n plus c2 1 minus root 5 by 2 to the power n. With boundary condition of f0 equal to 0 and f1 equal to 1, we can find the value of c1 and c2. Right? So after getting value of c1 and c2, we get Fn equal to this recurrent formula. So we can see here that if you just put direct value of n, you will get value of Fn directly from here. So no need of going back and forth. So another recurrence relation is like inhomogeneous recurrences, where right hand side is not equal to 0. And when right hand side is of the form Bn, Pn, Pn, where B is a constant and Pn is a polynomial of degree d. So this kind of recurrences will be also solved by this method. We solve left hand side as it is, and right hand side is equal to b to the power n Pn, right? So what will happen? So left hand side you will solve by same method, and right hand side will be x minus b to the power degree, where Pn is polynomial of degree d. So this will be d plus 1 equal to 0. For example, consider this recurrence. So if we put Tn equal to x to the power n, so left hand side will be x to the power n minus 2xn minus 1. So here will be x to the power n minus 1. Take lower order term outside. It will be x minus 1, not 0. So this is x equal to 1. So left hand side is x minus 1. So what will be solution? And this is Pn is a polynomial of degree 1. So this Pn is treated as 1. Clear? So now this Pn is treated as 1. Its degree is constant. It is a constant polynomial. Its degree is 0. So what is solution of left hand side? X minus 2. And solution of right hand side is x minus b. So x minus b degree is 0 plus 1 equal to 0. So this implies x is 2 and 3. So we have two roots of this equation. So solution will be given by Tn equal to c1 2 to the power n plus c2 3 to the power n. So this is solution of the particular recurrences. Clear? So now, from here, assume that T0 is 0. Assume that T0 is 0, right? So from here, T1 it will be 2T0 plus 3 to the power 1. So this is 2 times 0 plus 3, making it 3. Clear? So now here will be T0 is 0, we need two equations to evaluate two constants. So let's talk about T0. C1 2 to the power 0 plus C2 3 to the power 0. This implies 0 equal to C1 plus C2, calling equation 1. Clear? And now T1 was 3. We compute T1 by this method. So T1 is 3. So 2C1 plus 3C2. This is equation number 2. So if you want to solve this equation, just multiply by 2. So we'll get 0 equal to 2c1 plus 2c2, 3 equal to 2c1 plus 3c2. You just like subtract it, so c2 equal to 3. And if you put c2 equal to 3, what we will get? C1 equal to minus 3. C2 is 3, so C1 is minus 3. So solution will be Tn equal to minus 3 to the power n plus 3, C2 is 3 and 3 to the power n. So in fact this is big O of 3 to the power n plus 1 actually. So this is how we are solving the recurrences by characteristic method. So another method to solve the recurrence is master method. As its name suggests, it is master to all of the method. So what is a general form of the recurrence relation in master method? This should be Tn is A_Tn by B plus Fn. So that here problem is divided into a part. Actually, a greater than or equal to 1. Mostly we are using this master method in the divide and conquer approach. So problem is a greater than or equal to 1 and b is strictly less greater than 1. Because if b is minimum 1, this side is not going to decrease. So this side has to be less than left hand side. So this A and F is any asymptotic positive function, and generally we call this side as time to divide the problem, and this is time to combine the problem. Actually this is the combine the problem. Yes. So this is how we are treating the master method. So a greater than or equal to 1 and b should be strictly greater than 1, and this should not be a negative number, this should be a positive function. So master method has 3 cases. So you see, for example, in this situation, a is 4 and b is 2 and Fn is n. So and you know that what we are going to check only a greater than or equal to 1, and this guy should be greater than 1, and this should be positive function. Clear? So this should be positive function. If this satisfies, that means this is a like case of the master method. So it's clear. On the other hand, suppose if we write Tn equal to 4Tn by 2 plus n, this. So if see whether it is recurrence relation or not. So if you just write Tn 4T 3n by 2 plus n. So converting into this form, Tn is A_T n by B plus Fn. Suppose we want to convert this into this form. How to convert it? 4T n by 2 by 3 plus n. And we know that this 2 by 3, this guy is less than 1. So that means this is not going to be the recurrence relation. This is not a part of the recurrence relation. So this type of cases should be cancelled out. So we cannot solve, in fact no method can solve this type of recurrence relation because it is not even recurrence. This side is not in decreasing, this side is increasing. So 3 common cases you see here. Again, Tn is A_Tn by B plus Fn. So what we are going to do in all these 3 cases, 3 master cases of master method, we are going to compare this Fn with n to the power log A and base B. This is the comparison method. So in case number 1, what we are going to have, if this guy is less than big O of n to the power log A base B minus epsilon, for epsilon very small positive quantity. If this is less than this, then solution to the recurrence Tn is theta n to the power log a base b. This is direct solution. No need to solve it again and again. So you will get the direct solution of the method. Okay. So in fact, what we are going to have, we are just going to compare this Fn whether this is less than with n to the power log a base b. This is the shortcut method, even if you are not going to compare. So for example, see this Tn is 4Tn by 2 plus n. So a like n, Fn is n here, clear? And we go of n to the power log a is 4, b is 2 minus epsilon. So now left hand side is n, right hand side is n to the power 2 minus epsilon. So we have many choices for epsilon here. We can choose epsilon 1 or we can choose epsilon equal to 0.1. So in fact, then in this situation, n is always less than this guy. We are going to subtract, not equality. BIGO in general, BIGO is stand for equality also, but this is clear that n to the power 1 is always less than something over here. So that means this is the case of master method 1. So solution is very easy. Tn will be whatever is written over here, this will be the solution. Yes. We just remove the epsilon. So this case 1 is very, very clear. So let's have another example. See, Tn is T 2n by 3 plus 1. So if you just convert this guy, Tn is T n by 3 by 2 plus n. And here b is 3 by 2, definitely. And a is 1. A is 1 here. And b is 3 by 2. This is greater than 1 and this is greater than or equal to. And that means this is the case of master method. So let's start with case number 1. N is BIGO of n to the power log a is 1 and b is 3 by 2. So this is like minus epsilon. That means, is it possible that n to the power 1 is less than like this? N to the like this is 0 minus epsilon. So n cannot be less than n to the power 0 minus epsilon. That means this method, case 1, is not applicable over here. So master method case 1 failed over here. So let's have another example. So whether master method case 1 is applicable over here or not. So see, Fn is n square here in this recurrence and BIGO of n to the power log a is 7 and b is 2, clear? And minus epsilon. So we are going to have this. Log 7 base 2 is definitely more than 2 because, log 8 base 2 is 3. So this is close to, this value is close to 3 something. So we are working. So if you can see this is close to 2.81 minus epsilon. And now this is 2. So what will happen? This 2 is always less than 2.81. So we can get some epsilon. Let's say epsilon is 0.1. This must be greater than 0. So that means this is case of master method. So answer is very easy. Whatever this is 1, we are getting the answer. So this is n to the power 2.81. So this is very popular method. Actually, this recurrence is the recurrence for Stresson's matrix multiplication. We'll see it later. Yeah. So another case number 2. Case number 2 is saying that case number 1 was BIGO and case number 2 will be theta and case number 3 will be omega notation. So in this case, if Fn is theta, that means equality n to the power log a base b. If this is the situation, then Tn will be the same thing is written over here, appended with log n base 2, where this log is base 2. Actually, this is base 2 log. So if this is the situation, then we have case 2 of the master method. For example, suppose this is the situation, this is the recurrence relation. Here, Fn is n square is theta n to the power log A. A is 4, B is 2. Yes. So here n square equal to theta n square. That means this is equal. N square equal to n square. So that means case 2 is applicable. So what is solution? Solution is very easy. Tn will be theta. Whatever we have here, n square, this is appended with log n base 2. So this is very easy method for solving the recurrences, right? Let's see this whether case 2 is applicable over here or not. So now this Fn is n cube and now theta n to the power log A. A is 4 and B is 2. Yes. And in fact, n cube cannot, and this is theta n square. And this is n cube. So in fact, n cube is not equal to n square. Even case 1 is not applicable because n cube is not less than n square. So that means case 1, case 2, both are not applicable over here. Both methods are case 1 and case 2 cases. These two cases are not applicable in this kind of recurrences, right? So there is extension of master method 2, case 2. Let's have that extension. So, so this is extension. Generally, it is not covered under the master method. So this is just to solve the recurrences. If Fn is same thing, n to the power log A base B, we are just adding log Kn, where this K is greater than or equal to 0. If this is the situation, then Tn is same value, this, and whatever K we have, this is increased by 1. So same question, all the questions can be solved by this method also without any problem, like here. See this, n square is theta n to the power log A. A is 4 and B is 2, right? So we can take log 0 n without any problem. Here K is 0. Yes, this is equal. So n square equal to theta n square. So what is K? K is 0 here. So answer will be K plus 1. So answer is the same. So Tn will be theta n square, and whatever K we are choosing, that is incremented by 1. So log K plus 1. K is 0. So this is 1. So we'll get the same answer, Tn n square log n. Yes. So it's not having any issue. But this method this is also not going to be solved by the method, right? So okay. Let's have another example of this extension, like, yes, like see here, if we are talking about Tn, 4Tn by 2 plus n square log n. So generally, in the examination, one question is coming that whether case 2 is applicable or not. So in fact, case 2 is not applicable on this recurrence. However, this can be solved by extension of case 2. But in fact, case 2 cannot solve, right? So here n square log n base 2, this is equal to theta n square, right? Log A base B, and now n square. So you can write here log n base 2. So K is over here is K is 1. So that means if you just K decide the value of K, so Tn will be given by theta. Whatever K you have chosen, it is like K plus 1. Answer will be n square log K plus 1 is log square n. So this is the solution of the recurrence. So that means master method extension is very popular, especially if you have question like this, right? Where equal case 1, case 2 is not applicable. So you can go ahead and use this extension method, right? Yeah. So now let's talk about case 3 of the master method. So what is case 3? And in case 1 is talking about big O, case 2 is talking about theta, and comparison is always with n to the power log A base B. So case 3, we are talking about omega, lower bound over here. So you know, if Fn is omega n to the power log A base B, and case 1 minus epsilon, case 2 no epsilon, case 3 is plus epsilon. So if this is the situation for some epsilon greater than 1, 0, and together with this, right, if you are going to apply the case 3 of master method, make sure that regularity condition is also going to be satisfied, right? So what is regularity condition? A f n by b less than or equal to C into Fn, where restriction on C is that this must be, C is a constant which is less than 1. This must be less than 1. So this is known as regularity condition. So both conditions must be satisfied in order for case 3 is applicable. So if this is the situation, then Tn will be theta of Fn, right? So then in that situation, Tn will be theta of Fn. Clear? So no need of going with power. So that means this is what is its implication? That Tn is A Tn by B plus Fn. Its meaning is that this is asymptotically faster than this. That means this is having more time as compared to this guy. That's why we are always giving time in terms of this theta n. So this is having higher weightage than this. That means time of combining is more than time of dividing. That's why our time is coming in this ratio. Okay. So let's have an example that Tn is 4Tn by 2 plus n cube. We can in fact while solving the master recurrences using master method, it is always advised to start with case 1. If it is not applicable, check with case 2. If it is not applicable, it's better to go with the case number 3. So here case number 3, n cube, right? Omega of n to the power log A. A is 4 here and B is 2. Definitely this is n cube and this is n square. So you can go ahead, with epsilon. So that means it seems that n cube equal to omega n square plus epsilon. Yes, so it seems that epsilon can be 1. So now it seems that case number 3 is applicable. But we are not sure that case number 3 is actually applicable until we run the regularity condition. So what is regularity condition? Regularity condition is saying that A Fn by B must be less than or equal to C Fn, right? And Fn is n cube and A is 4. So here 4 into Fn is n cube. So Fn by 2, B is 2. So Fn is here n cube, right? So Fn by B, Fn by 2 is n cube by 8, right? So this is n cube by 8 less than or equal to C into Fn, right? Fn is n cube here. So now this is cancelled out. So 1 by 2 less than or equal to C. This implies that C equal to 1 by 2, which is less than 1. That means regularity condition is also satisfied. Clear? That means regularity condition is also satisfied. Therefore, Tn is given in Tn is directly proportional to Fn. Fn is n cube. So this is very simple method actually. So you can take another example here, like Tn is Tn is like 9t, let's say n by 2. 9t n by 2 plus, let's say this is n square, n cube. Yes. So if you go over here, so definitely you see here n cube is omega of n to the power log a is 9 and b is 2. Right? So a is 9 and b is 2 and c plus epsilon or minus. So let's see whether case 3 is applicable over here. Log 2 9 is definitely greater than 3. This is greater than 3 because log 8 base 2 is 3. So this case is not applicable. That means case number 3 is not applicable. Right? So you can see here this is another method, case 3 n square log n. So this is going to be the case number 2 of the master method. That is the end of the master method. So I hope you enjoyed my lecture. Thank you.